Hello all, good day. So this is a first official music video made with OpenAI Sora, which was published by this channel Washed Out, and it's actually quite amazing. We'll just look for 10 seconds. So you may not be able to hear the sound, but it's quite amazing how this generative models are able to create, this videos in such detailed clarity. Now, this is one such application, OpenAI Sora, but I'm pretty sure you would have used a lot of other applications like ChatGPT, DALL-E, Midjourney, Runway ML, who are doing incredibly great job in generating this images, videos, music, and whatnot. These are really cool. However, they can have some shortcomings, and I will just use these two examples to highlight few shortcomings they could have. Although this is an old example which may not exist now, but one very common shortcoming of ChatGPT like application is hallucination, where the model gives answers and it looks very real, very factual, but that could be actually nonsensical. For example, here on asking prove the dinosaur built a civilization, the model says some species of dinosaurs even develop primitive forms of art such as engraving on stones. So it looks very factual, but it's not true. And on asking Mid-Journey, this is again an old example. They would have definitely improved it. On asking for generating some party images, they generate this, which looks quite good. But when you look closely, you can see the arrangement of teeth is very weird. The finger sizes here, they're very weird. And here you could see that, there are more than there are like eight fingers in this hand. So this kind of mistakes are acceptable when you're just looking for some answers or generating this kind of art stuff. But just remember that AI is used in various other applications, and it's being used quite heavily, ranging from automated driving to medical diagnosis to disaster management, disaster prediction, to drug discovery, in the manufacturing industry, and even in robotics, uh, and eventually the robots which will be, interacting with us in the real world. Now, when this kind of AI applications are deployed in real world, they just don't need to perform the task. They need to, and they just don't need to give the predictions alone, but they need to be sure. They need to be reliable. They need to be trustworthy because these are quite critical applications. And as they will be used in the real world scenarios. There are a lot of uncertainties. So our world is full of uncertainties, and it could be natural uncertainties, or it could be some uncertainties that could be introduced by hackers or some other malpractices. And in such applications, such safety critical applications, having the reliability and trustworthiness measure in the predictions by this AI model is so crucial, because even a small mistake could lead to loss of lives. For example, in automated driving, or in medical diagnosis, or even in disaster management or disaster prediction. So this gets very important that these models are able to capture those uncertainties, and they're aware of when they are not able to perform well, and in which scenarios they're able to perform well. Now, this are two Instagram reels I grabbed from these two channel. So on the left, you will see a automated driving scenario where the steering wheel automatically turns left, and there is a car which is coming from left, and the driver is quite surprised why this happened. So this is kind of the uncertainty where, we need to be sure that this AI is quite reliable in this scenario. And another example is here, where this is another self-driving car, which then gets stopped by a person standing on the side, and we'll see why. Yeah. So you see that these uncertainties, or attacks could be done by artificially introducing such scenarios. Again, these are very critical for these AI applications, because in the context of driving, it could be quite fatal. Now, this is the reason why, we whatever AI applications that we develop, we deploy in real world, they need to be reliable and they need to be trustworthy. And that's why this topic is getting quite momentum. And one way to gain this reliability or trustworthiness in AI is through uncertainty estimation. And that's what we are going to see in the remaining of the talk. So let's get started. And in this talk, I'll be giving a high-level context of why we need uncertainty estimation in AI models and how and where, you can use them. The technicality of how to implement them, how to use them inside your model, we'll talk in the later videos. So the agenda would be we'll just talk in short background, the objective and the method that, about the uncertainty and in which use cases we can use them, and then we can conclude them. So let's take one example of AI diagnosis where there's an AI system which is deployed to diagnose any disease, which could be quite critical. And you have two models. Model A, which is 90% accurate, and whenever you feed the data, it gives answers all the time. It's a good 90% accurate. And model B, which is 75% accurate, but it gives answer, but along with answers, it also has it awareness of the scenarios when it does not know. So it will give you answer when it knows, and it will tell you when it does not know about the scenario. So which model, we should deploy in the real world? I am pretty sure you'd have guessed model B, although the accuracy is less, but it will be more reliable because it is not overconfident. It has the awareness of the scenarios where it knows that it does not know about. And there we could encounter in real world many such scenarios which could be new, which could be something which the model has not seen. And in those scenarios, having this measure of reliability, having this measure of awareness that when it does not know becomes quite important. And that's the reason why, we would go for model B in this scenario. Now, the objective or our objective generally for the safety critical applications should be to build a reliable and trustworthy AI systems. So I have taken some examples, there could be many other examples. So in such systems, what we need is not just prediction. So generally when we deploy a AI model, we give some input and we'll have a prediction. But along with prediction, we also need a measure of reliability that we can trust on the prediction, and we'll know when it encounters some scenarios that which it has not seen or which is very different. And this measure of reliability can be achieved by incorporating uncertainty estimation into your models. So uncertainty estimation will help you to quantify and give you a measure of reliability. It also is a measure of the trust of the AI system in its decision, whether the predictions that the AI system is giving can be trusted or not, and in those scenarios it can be passed over to someone else for taking decisions, and it enables the model to tell you that it does not know few answers or the situations where it does not know. So that's why uncertainty estimation gets very important for the safety critical estimation, because it gives this ability to measure the reliability of its predictions. Now, why do we need actually reliability in AI? I did not say it, but let's highlight these two examples we just saw. We need to have reliability in the AI systems because it's like it's life could be at stakes. Then there could be, as I said, the human incorporated attacks like this adversarial attack, where this model was predicting these as pandas, but by adding some noise or some code, it start predicting it as a gibbon. And another example is in this car detection AI system, where when this car is camouflaged, then it start predicting it as a cake. Now it is giving a 71% accuracy as a cake. Now here we need a measure of uncertainty that the model tells you that I'm not sure what it is, and maybe someone else takes the decision. So this is one reason why we need reliability, to obviously ensure the safety in the system itself. But beside that, we also need reliability from the business aspect and how our whole ecosystem is set up. So this is one report from the CAGR, and you can see the market share of AI being incorporated in the automotive industry. It's going to increase exponentially. It's going to be, a lot of features in the automotive would be AI based, and safety is very much required. And also there are new ISO standards coming up for AIs for the functional safety in road vehicles, like ISO 8800, ISO 4804, which would be compatible with the existing, functional safety standard like ISO 26262 or 21448. And it's just a matter of time when, different automotive bodies like Euro NCAP or Bharat NCAP make this rule that we need to follow these standards or the vehicles won't be passed. So from the business or the ecosystem aspect as well, we need to incorporate this reliability or safety measures in the AI systems wherever we implement them. So this is another example, of some in March 1 where there was some wrong information generated by the generative model, and the it was mandated that the AI platforms, they need to get a government approval for these AI models. Later it was revised that the government stated the under-tested or the unreliable AI product should be labeled with disclaimer indicating that the output generated by such products may be unreliable. So you could see, how everything will come under certain regulations, and this will become compulsory. So it's better that we incorporate such safety systems into our AI models. And again, why we need reliability? One very famous example is the Tesla autopilot system in 2016 when it crashed into a trailer. And what happened was, according to the reports, the AI system thought that this trailer was a sky, and it could happen, because as I said, there are a lot of uncertainties in the real world when we deploy such AI systems. We live in a very crazy and uncertain world. And why such thing happens, like one example I could give you. So when we develop these AI models, let's say we are doing a car detection or car classification, we collect some data, we train the AI model, it's performing very well, then you deploy it in the real world. And in real world, you encounter some car like this, which has wings, and which your model is not trained on. And in this case, model need it's very necessary that the model tells you that, I don't know about this. Or you come across this crazy banana car, which then the model will be confused. Is it a banana? Is it a car? And it could be again proving fatal. Another example, let's say you're doing a cat or dog classification, and with the advent in biotech or synthetic biology, some new species are developed, and or the model was deployed in some other place where there are some new species and the model does not know. So it need to be aware, when it does not know, or someone shaved the cat and it becomes a totally different species now. So in such scenarios, there are a lot of uncertainties that are circulating when we deploy these AI systems in real world. And those uncertainties need to be captured and the model need to be aware by those. And why such thing happens, as I have already told you, there are limitations in our ability to observe the world. We cannot observe everything about the world. The world is very uncertain. And then there we have even if you observe it, we also have limitations in our ability to uh, model the world or model the task of the world that we are doing. And also because of innate non-determinism. So there are a lot of stochasticity and uncertainty everywhere around. We cannot predict everything very confidently. So that's the reason why we need to have this measure of uncertainty, measure of reliability in AI to handle this kind of uncertainty, especially in the real world applications. And as I expressed, the safety, even the standards that are coming up, this is one example for the automotive domain, but I think even for other domains, there will be some standard coming up where AI systems need to adhere to these safety or reliability measures. And the whole idea being to reduce the risk, and the root causes being unseen data, overfitting, data imbalance, error in measurement, which we'll talk about. Now, coming to the method, so we discussed about our objective. We need to have this reliability for safety critical applications. We know that the world is uncertain. We are not able to model everything. But uncertainty, we saw one example, when we deploy the model like for the car or the cat dog system. But the uncertainties actually can get induced in different stages of the entire AI development cycle. So if I just categorized the development cycle, we have data acquisition where we acquired, prepare data, then we have AI model designing, training, and then we have the deployment or the inference. Now, let's see, and in each different stages, how these uncertainties can get introduced. So one is in the data acquisition. So we have lot of variability in the real world data itself. For example, there are, numerous species of cats, dogs, etc, and these variations could also incorporate in uncertainty. We'll not be able to capture everything, and so this is one way. And another is the error or noise in the measurement system itself. So for instance, this camera that we are using for capturing the images. Let's say it has a lower resolution. So whatever data that we capture is actually not a good data. It is a noisy data. For instance, here the dog image is blurred, and this could cause some kind of uncertainty or randomness in the result, or our lack or our mistake during the labeling. Let's say we did not define labeling properly. This image is both cat and dog, and someone label it as a cat, someone label it as a dog. So there is another uncertainty, or even due to the class overlap. Maybe there are a few examples which look like both cat and dog, so there are overlapping. So there are uncertainties in the data, just by the nature of the data or by the uh, sensors that we use to capture those data. Then there are uncertainties during the model design and model training. So there are number of methods now to model the task to be done by the AI. And there are different architectures. Each architectures have different layers, etc. And based on what you choose, what method you choose, what architecture you choose, the model is going to converge to a different solution, slightly different, or maybe a different solution, which then again expose the stochastic nature of these models. Then there are uncertainties even during the training procedure. So depending on what hyperparameter you're choosing, the batch size, learning rate, optimizer, this all are going to influence what functions your neural network are going to converge to. And this all can introduce uncertainties during the design or the training itself. And then obviously, as we talked about, when we have trained this model, when we deploy it, there are high chances that we could come across unknown data or totally unseen data. For example, here there is a cat which looks like a towel, or here a cat sitting on a white blanket looking like some celestial object, or it could be totally out of domain data. For example, you train a model for cat and dog classification, and your image system is capturing a bike, and it should what it should do with it. So these all are different scenarios of uncertainties that could get introduced during different stages of AI development cycle. And it becomes very important again for the safety critical application, especially, that we capture all these different uncertainties individually or totally as a whole, and the model is aware that there are these uncertainties while taking the decisions. So in literature, generally we can classify uncertainties in two categories. So the uncertainties which are inherent in the data are due to the census limitations or error, they are called as the data uncertainty or the aleatoric uncertainty. Now, this uncertainties cannot be corrected unless the data itself is improved. So, the data or the sensor is improved. And then the other uncertainty that is due to the lack of the knowledge of the model. If the model is lacking the knowledge about the data, or uh, it still needs to learn, it is called as the model uncertainty or the epistemic uncertainty. So these two are like major categorization of the uncertainty that people try to model in their AI systems. There are different approaches for uncertainty estimation. I'm just listing few of them, but will not go into them right now. I'll just paint a general idea of how you can model this uncertainty or how it is being modeled. So for the uncertainty which is inherent in the data due to sensor limitation, that is the data uncertainty, you can capture it by modeling a distribution over the model's output. And for the uncertainty due to the lack of knowledge of the model itself, that can be modeled by modeling a distribution over the model parameters. So let's say we have this neural network which is parameterized by theta. We have x and then output y. So generally, when we model like deterministic model, we'll have just a single output y. So what you can do here is, instead of having a single output, you can have a output distribution here, which is giving the full distribution of the output. For instance, let's say it's a Gaussian distribution, then the mean of this distribution could give you your output, and the variance of this distribution could give you the uncertainty or related to that predicted output. And if you model, so here again in the deterministic model, we'll have a single theta parameter, but if you model your if you model a distribution over the parameters, then here with this distribution you could capture your lack of knowledge of the model itself. So that's the knowledge uncertainty. One simple example to understand this both knowledge and sorry, yeah, model and data uncertainty is just consider example of ensemble of model. So let's say you have three models, and each model is predicting output distribution. So this is the model which has mean and variance, mean being the output of the model and variance being the uncertainty. Same for model 2, model 3. So if you want to capture the data uncertainty, which is being predicted in the variance of the output, you could simply take the mean of all these variances. That would give you your data uncertainty. And for knowledge uncertainty, you will take a variance among this predicted output, which is the predicted mean. So you know how much confident each of this model are in their predicted output. That can give us uncertainty in the knowledge gained by the model. So for instance, if all the three models are predicting as cat, 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 then there will be no variations. We know that, it's a cat. But let's say if one is predicting as a dog, one is predicting as a cat, another is predicting as a dog, then we know it's more uncertain because not, all the models are sure about it. Maybe it's a, different species of cat or something which the model has not seen. So this is one way you can capture both data and the model uncertainty. Now let's come to, use cases of how and where, we can use this estimated uncertainties. So we can use these uncertainties in making your final decisions, in decision making, and to ensure the reliability or trustworthiness of those decision or those prediction. And then we can, despite that, we can also use them for the data preparation and the model development. For example, we can use them for efficiently labeling your data and in the active learning regime. Then we can use uncertainty estimation in understanding the results and also monitoring them. For example, to identify the corner cases, to identify out of distribution samples, and even to identify if your, there's a shift in your distribution, the data on which the model you trained, whether it has changed over the period of time. Let's see a few examples of this. So this example of using uncertainty estimation for reliability and decision making. So this example of object detection. So you can see here, this is the predicted probability and this is the measure of certainty or uncertainty. It's very certain, so we are very sure it's a car. Here you can see the probability is good, but you can see it's quite uncertain about it. So here we need to be very sure. We need to be very sure that if it's a very critical application, then do we rely on the model output or not? And here you can see even the score is less and even the model is uncertain. So based on this uncertainty, you can take your final decision of what to do with the predicted output from the model. Another very interesting example is in the manufacturing. So this is a data set for surface defect detection. And you could see these are the predicted probability for all these samples. This is not a defect, not a defect, and these are the probability scores. But when we pull up the uncertainty score, so this says this is not a defect, very right, and the predicted uncertainty is also very less, so it's totally fine. But this is an interesting case where the model thinks that it is not a defect because it looks actually quite good, but the uncertainty measure that we incorporated is slightly higher. So when we pull up the actual label for this image, we see that there is a defect, which is here, which is quite subtle, maybe missed by the model, but because of the uncertainty measure, we'll be able to, have a cross check of whether to relying on this decision or not, and it can help in your decision making. Here again, it's very clear that it's a defect, and even the uncertainty is low, means very certain it's a defect. Here again, it says this is a defect, maybe because of this, but yeah, this is example of this one, the defect one, and this is again it says defect, but you could see that the uncertainty is high, and when we check, actually this is not a defect, this is some, some other stuff. But what I'm trying to say is, uh, when the uncertainty is high, then we, for the decision making, this can be passed on to actual, the inspector in the plant where he can take a decision. So that's the advantage of incorporating uncertainty. It can help you to take decisions in such scenarios where it could be critical, For the things, for the cases where you're very sure, we can go ahead with the AI models. But the cases we are uncertain, we can have a double check or we can let the human inspector make the decision. And another use case of uncertainty estimation is in the corner cases identification. So corner cases are those which are in between. Let's say you're classifying defect and non-defect. And there could be some cases which looks like defect or but could be non-defect, or it is something which it's very tough for the AI model to learn. For example, this is not a defect, very straightforward, but even this is not a defect. But you can see that it looks something like line or crack, or this image where half of it is very different. This is very much defect. This is non-defect, but there is some patch. So we can identify these corner cases by measuring their uncertainty. So the corner cases will be having the higher uncertainty, and it can help to understand your data or problem better. And also for decision making, this all samples could be passed to the human inspector to take final decision. So another use case, as I said, is to identify the corner cases. Another very interesting application of AI could be for labeling and in the active learning. So this is another example of defect detection on magnetic tiles. So here you want to identify defects on the magnetic tile. Now, suppose these are the labels, but imagine these labels were not given to you, and you don't know which samples to label. You have millions of samples. How would you decide which samples could be important for the AI model to learn from? Like on which sample it could learn better and faster. So one such application could be to save your labeling cost will be based on the uncertainty estimation. One example I'll show you how it is used in active learning. So let's say you have few samples which are labeled like 100 samples, and you train some models. Then you have remaining new samples that have come from the next batch of production, and you don't know which is defect, which is not defect. But how will you decide which could be the more informative samples? So that's where you can pass this new samples through your model and measure the uncertainty, and based on the uncertainty we can identify informative samples. So these informative samples are the one which tells that on which samples the model could learn faster. And then instead of giving everything for labeling, we can consider these informative samples for labeling, and then the labeler could label this samples, only these few samples or few hundred among the million. Then this could be fed into your training loop, and in this way iteratively we could learn from the informative samples rather than using all the samples. And it could reduce your labeling cost. It could speed up your development cycle. So this is another example of where this uncertainty estimation could be used. And it can be used for detecting your data drift if your distribution of data has changed. For example, you develop a model to identify this kind of defects, and after a year you start realizing that there are some new kind of defects coming. So this, with a measure of uncertainty, you will be able to identify that there is a distribution shift on the model, on the data on which the model was trained, and the new data. So you may need to retrain your model with this new type of data which is coming, because the data distribution has shifted. So it can help in doing that. Another example is, suppose you develop a parking system here and you come across totally new parking sign, or maybe this model is deployed in some other city which has some other language. So here the data distribution has shifted. This is very unknown to it. So in these cases, uncertainty estimation can help you identify how the model is performing in real world over time. And if over time, if the data distribution is shifted, then we may need to retrain these models. Another example could be you training a simple cat versus dog classifier, and you deployed it in some wildlife monitoring system, and you encounter some totally different species. So this all kind of uncertainties could be captured by the uncertainty estimation, and it could help us to develop more reliable AI systems. So that's what we discussed about, where uncertainty estimation could be used for your decision making, for measuring reliability, for efficient labeling, for active learning, for corner case identification, for distribution shift, for out of distribution detection. And these are few references. I will also give more references in the description, where you can, you know, read how to implement this uncertainty estimations in your models. And to conclude, uncertainty estimation plays a major role in meeting the upcoming AI safety standard or other government regulations that will come in. For safety critical application, estimating the predictive uncertainty is required as a measure of AI systems reliability. Estimating both data and model uncertainty is essential throughout the development cycle, from data acquisition to inference. Uncertainty estimations are highly important in decision making, that is, when to trust the prediction from the model or when to defer the decision making to a human. Beside reliability measures, as we discussed, uncertainty estimation can also be used for out of distribution detection, data drift detection, active learning, efficient labeling, and maybe more of features. So this was a very short or high-level summary of where and how we can use uncertainty estimation, and actually it's quite important that as these AI systems get deployed in real world, we have this kind of reliability checks for the decision made by the systems. And I would like to thank you for your attention and conclude stating Stephen Hawking's statement that success in creating AI would be the biggest event in human history. Unfortunately, it might also be the last unless we learn how to avoid the risks. Thank you for listening and keep learning, keep exploring neurons. Bye.